Momentum analysis of flow systems. This topic introduces momentum analysis as a primary tool to analyze forces generated by fluid flow. The main focus is to relate changes in fluid momentum to the forces acting on a system. This approach is essential for analyzing pipes, nozzles, turbines, and other fluid machinery. The momentum concept will be used within the control volume framework. The entire discussion forms the foundation for understanding flow-structure interaction.
Lesson Plan: Fluid Mechanics 1. The course structure is arranged progressively from basic concepts to advanced applications. The early chapters build understanding of fluid properties, statics, and kinematics. This is followed by energy and Bernoulli equations as the foundation of flow analysis. The momentum chapter serves as a bridge between energy analysis and force analysis. This sequence ensures students understand flow from both energy and force perspectives.
Learning outcome. The learning objectives emphasize the ability to identify forces and moments acting on a control volume. Students are expected to use control volume analysis to determine forces caused by fluid flow. In addition to forces, moments and torque are also important in rotating systems. These competencies are highly relevant to engineering applications, such as pipes, pumps, and turbines. The final goal is the ability to analyze flow systems in a comprehensive way.
Linear momentum. Linear momentum is defined as the product of mass and velocity with the same direction as the velocity. The larger the mass or the velocity, the larger the momentum of the object or flow. This concept is important because changes in momentum are directly related to force. In fluid flow, momentum is used to analyze forces on bends, nozzles, and supports. This becomes the foundation of all force analysis due to flow.
Newton's second law. Newton's second law states that the net force equals the rate of change of momentum with respect to time. If the mass is constant, this reduces to F equals ma. In fluid flow problems, the form used is F equals d of mv dt. This equation becomes the bridge between particle mechanics and control volume analysis. With this approach, forces in flow systems can be computed systematically. Check your understanding, number 1. The net force on an object equals the rate at which momentum changes, and it depends on the object's mass and how quickly velocity changes over time.
Angular momentum. Angular momentum is the rotational analog of linear momentum. The net torque causes a change in angular momentum over time. The magnitude of angular momentum depends on the moment of inertia and the angular velocity. This concept is crucial in the analysis of turbines, pumps, and other rotating systems. This relationship shows that torque plays a role similar to force in rotational motion. Types of control volumes. Control volumes can be fixed, moving, or deforming. Fixed control volumes are commonly used for stationary pipes, nozzles, and turbines. Moving control volumes are used for vehicles or translating systems. Deforming control volumes are used for pistons or balloons. This classification helps in choosing the simplest and most effective analysis approach. Control volume forces. The forces acting on a control volume are divided into body forces and surface forces. Body forces act throughout the fluid volume, with gravity being the most common example. Surface forces act on the control surface, mainly due to pressure and shear stress. Both types of forces must be summed to obtain the total force on the system. This force balance is then related to the change in flow momentum. Check your understanding. Number 2. Which of the following statements correctly describes surface forces in a system? Correct answer: B. Surface forces act on the control surface due to pressure or shear stresses.
Explanation of incorrect options. Option A. This is incorrect because body forces, not surface forces, are caused by fields like gravity and act throughout the control volume. Surface forces specifically act on the boundaries, control surface. Option C. Surface forces do not create a gravitational field. Instead, they act on the control surface due to external pressure or shear stresses. Gravitational fields are related to body forces. Option D. This is incorrect because surface forces act on control surfaces, which could include fluids, not solely on the boundaries of solid objects. Surface forces are not restricted to solids.
Gravitational force on fluids. Gravitational force acts on every small fluid volume element and contributes to the weight of the fluid. The direction of this force is always downward, usually defined as the negative z direction. The magnitude of the gravitational force is proportional to the fluid density and volume. In control volume analysis, this force is included as a body force. Its contribution becomes important, especially in flows with elevation changes.
Surface force components. Surface forces can always be decomposed into normal and tangential components. The normal component acts perpendicular to the surface and is directly related to pressure. The tangential component acts along the surface and comes from shear stress. The chosen coordinate system affects the component values, but the resultant force remains the same. This concept is very important in analyzing forces on walls and solid boundaries.
Check your understanding number 3. Surface forces are decomposed into normal components, which act perpendicular to the control surface, and tangential components, which act along the surface due to shear stresses.
Stress tensor components. The state of stress in a fluid element is represented using the stress tensor. Normal stresses act perpendicular to a surface and indicate compression or tension. Shear stresses act parallel to a surface and indicate shear deformation. With this representation, all internal force components in a fluid can be analyzed systematically. This concept forms the basis for understanding force interactions inside a flowing fluid.
Atmospheric pressure effects. Atmospheric pressure acts equally in all directions. In many analyses, the effect of atmospheric pressure cancels out and doesn't need to be included explicitly. Therefore, gauge pressure is often used to simplify calculations. With this approach, only pressure differences contribute to the net force. This makes the force analysis on control volumes simpler and cleaner.
Control volume selection. Choosing an appropriate control volume can greatly simplify the calculation process. Two different control volume choices can lead to very different levels of analysis complexity. A good control volume usually minimizes the number of unknown forces. In addition, the boundaries should cut the flow where velocity profiles are simple. This strategy makes the momentum equation easier to apply.
Linear momentum equation. The linear momentum equation is derived by applying the Reynolds transport theorem to momentum. Momentum is defined as the product of mass and velocity. In control volume form, this equation relates the total force to the momentum change within the volume and the flow across the boundaries. This form is well suited for analyzing real flow systems, such as pipe bends and nozzles. This equation is the core of all force analysis due to flow. Check your understanding. Number 4. What is the primary purpose of applying Reynolds transport theorem to momentum? Correct answer, C. To track changes in momentum within a control volume and across its boundaries. Explanation of incorrect options. Option A. This is incorrect because Reynolds transport theorem, when applied to momentum, does not deal with energy and heat transfer. It specifically tracks momentum changes in a system. Option B. Momentum is not expressed as the product of force and displacement.
Instead, it's expressed as the product of mass and velocity. This makes the statement incorrect. Option D. While Reynolds' transport theorem can analyze properties like mass, the focus here is on momentum, not on changes in mass density over time. Force balance in flow systems. In flow systems, the total force usually consists of weight, pressure forces, and reaction forces from supports. To simplify the analysis, atmospheric pressure is eliminated by using gauge pressure. The reaction forces from supports appear to balance the forces caused by the flow. All these forces are then related to the change in fluid momentum. With this approach, the forces acting on pipes or fittings can be computed systematically. A control volume may have more than one inlet and outlet. Each inlet and outlet has its own mass flow rate and average velocity. To simplify calculations, average velocity is often used at each cross-section. With this approach, the momentum contribution of each stream can be computed separately. All these contributions are then summed in the momentum equation. Uniform flow examples. In many practical cases, the flow can be assumed to be uniform across a cross-section. Examples include well-rounded pipe entrances, the test section of a wind tunnel, and free jets in air. The uniform flow assumption greatly simplifies momentum calculations. With this assumption, the velocity is considered constant over the entire cross-section. This eliminates the need to integrate the velocity profile. Laminar flow profile. In fully developed laminar flow in a pipe, the velocity distribution has a parabolic shape. The maximum velocity occurs at the center line of the pipe, while the velocity at the wall is 0. The average velocity is smaller than the maximum velocity and is used to compute the flow rate. This profile shows that real flows are not always uniform. Understanding this profile is important for more accurate momentum analysis. Check your understanding number 5. In fully developed laminar flow, the velocity distribution takes a parabolic shape, with the maximum velocity occurring at the pipe's centerline. Flux balance. The net force on a control volume is determined by the difference between outgoing and incoming momentum fluxes. In steady flow, there is no accumulation of momentum inside the control volume. Each inlet and outlet contributes momentum according to its mass flow rate and velocity vector. The velocity direction is very important because momentum is a vector quantity. This equation becomes the practical form of the momentum equation for many engineering applications. Single inlet, outlet flow. The simplest case is a control volume with one inlet and one outlet. In this case, the momentum equation becomes much simpler. The mass flow rate at the inlet and outlet is the same for steady flow. The net force depends only on the change in the velocity vector between inlet and outlet. This model is very often used to analyze nozzles, diffusers, and simple bends. Reaction force in flow. A change in the flow direction produces a reaction force on the supporting structure. This force can be computed using vector addition of momentum at the inlet and outlet. Even if the speed magnitude is the same, a change in direction still produces a change in momentum. Therefore, pipe bends always experience forces from the flow. This analysis is very important for pipe support design. Rocket thrust mechanics. Rocket thrust is generated by accelerating the fuel from rest to a very high speed. The exhaust gases leave at a very high velocity, producing a large change in momentum. This momentum change creates a reaction force that pushes the rocket upward. If this force is larger than the weight of the rocket, liftoff occurs. This example shows a direct application of the momentum principle in engineering. Check your understanding number 6. What key factor enables a rocket to generate thrust for liftoff? Correct answer, B. The acceleration of fuel from rest to high speed, producing an upward thrust. Explanation of incorrect options. Option A, rockets rely on thrust, not aerodynamic lift for liftoff. Aerodynamic surfaces play a minor role during launch compared to thrust generated by fuel combustion. Option C, changing the launch angle does not reduce gravity's effect. Gravity remains constant. Thrust, not angle, is the key factor for overcoming gravity. Option D, rapid cooling of exhaust gases is unrelated to thrust generation. Thrust depends on the high-speed expulsion of hot gases, not their temperature after combustion.
Wind turbine forces. Wind turbine towers must withstand very large forces and moments due to wind pressure. The aerodynamic load increases with the square of wind speed, so the structural design must be very strong. In addition to horizontal forces, bending moments on the tower are also critical. Momentum analysis helps estimate the loads transferred from the airflow to the structure. Therefore, wind turbine design strongly depends on flow force analysis. Angular and linear motion. Angular velocity relates angular displacement to time in circular motion. The linear velocity of a point on a rotating body depends on the angular velocity and its radius. For the same angular velocity, a point with a larger radius has a higher linear speed. This relationship is very important in analyzing rotating systems such as turbines and impellers. This concept forms the basic link between translational and rotational motion. Linear angular analogy. In many aspects, translational and rotational systems have a strong analogy. Mass in translational motion plays a role similar to moment of inertia in rotational motion. Force corresponds to torque, and velocity corresponds to angular velocity. Linear momentum also has an analog in the form of angular momentum. This analogy helps simplify the understanding of equations and concepts in rotational mechanics. Angular momentum basics. Angular momentum is defined based on mass, radius, and angular velocity. Its value increases if the radius of rotation or the angular speed is increased. In real systems, the moment of inertia is used to represent the mass distribution relative to the axis of rotation. This concept is very important in the analysis of turbines, pumps, and other rotating systems. Angular momentum is a measure of a system's tendency to keep rotating. Check your understanding number 7. Angular momentum depends on mass, radius, and angular velocity, and increases with a larger radius or faster rotational speed. Rotating shaft dynamics. Angular velocity is often expressed in RPM and can be converted to radians per second. The power transmitted by a rotating shaft depends on the torque and the angular velocity. The larger the torque, or the higher the rotational speed, the greater the transmitted power. This concept is very important in the analysis of machines and power transmission systems. Rotating shafts are key components in many engineering machines. Force moment analysis. The moment of a force is defined as the rotational effect of a force about a point or an axis. Its magnitude depends on the force magnitude, the distance from the reference point, and the angle between the force and the moment arm. Mathematically, the moment is expressed as the cross product of the position vector and the force vector. This concept is very important in the analysis of equilibrium and rotational motion. In fluid systems, force moments are often related to shaft torque. Right-hand rule for moments. The direction of the moment vector is determined using the right-hand rule. The fingers of the right hand are curled in the direction of rotation, and the thumb points in the direction of the moment vector. In this way, the direction of the moment can be determined consistently in three-dimensional space. This rule is very important when working with vector cross products. Without this rule, the sign and direction of moments can easily be confused.
Angular momentum equation. The angular momentum equation is derived by applying the Reynolds transport theorem to angular momentum in a control volume. In per unit mass form, angular momentum is expressed as the cross product of the position vector and the velocity vector. This equation relates the net torque to the rate of change of angular momentum in a control volume. This form is very useful for analyzing rotating machines and flows with rotational effects. It is the rotational analog of the linear momentum equation.
Check your understanding. Number 8. What does the Reynolds adaptation for angular momentum primarily analyze? Correct answer? C. The changes in angular momentum within a control volume and across its surface. Explanation of incorrect options. Option A. While angular and linear velocities are related, this option does not involve the Reynolds adaptation, which focuses on tracking angular momentum, not velocity relationships. Option B. Angular momentum per unit mass is expressed as the cross product of position and velocity vectors, not simply their product of magnitudes. This oversimplifies the concept. Option D. The Reynolds adaptation does not deal with density distribution, but specifically analyzes angular momentum changes within and across the control volume.
Lawn sprinkler dynamics. A sprinkler system demonstrates how fluid angular momentum can produce rotational motion. Water ejected from the sprinkler arms generates reaction forces that cause rotation. The larger the flow rate and exit velocity, the larger the torque produced. This example shows a direct application of the angular momentum principle in everyday systems. This mechanism is also similar to the working principle of reaction turbines. Net torque in steady flow. In steady flow, the net torque is determined by the difference between outgoing and incoming angular momentum fluxes. There is no accumulation of angular momentum inside the control volume. Each inlet and outlet contributes angular momentum according to its mass flow rate and velocity vector. This equation forms the basis for torque analysis in rotating fluid machines. With this approach, shaft torque can be computed from flow data.
Centrifugal pump design. A centrifugal pump works by accelerating the fluid using a rotating impeller. The fluid enters through the center and is then pushed radially outward before leaving the casing. The kinetic energy given by the impeller is then converted into pressure energy. This process can be analyzed using the angular momentum principle. Pump design strongly depends on the relationship between velocity, torque, and fluid momentum change.
Impeller control volume. The fluid velocity inside an impeller can be decomposed into radial and tangential components. The shaft torque arises from the change in fluid angular momentum as it passes through the impeller. The inlet and outlet flow angles strongly affect pump performance and efficiency. By defining a control volume around the impeller, the angular momentum equation can be applied directly. This approach is the foundation of modern turbine and pump analysis.
Rotating lawn sprinklers. Rotating sprinklers are designed to distribute water uniformly over a large area. The rotation is generated by the reaction force of the water being ejected. The higher the water velocity, the higher the rotational speed of the sprinkler. Its working principle can be fully explained using the concept of angular momentum. This system is a simple but very clear example of fluid mechanics application.
Check your understanding. Number 9. Rotating sprinkler heads ensure water covers a large area uniformly by using angular motion driven by water ejection velocity and reaction forces. The main reference for this material comes from the book by Chengle and Jimbala, which is one of the standard references in fluid mechanics. All figures and main concepts are based on this source.
This book provides a strong theoretical foundation and many engineering application examples. By mastering the material from this reference, the understanding of momentum analysis becomes very solid. This reference is also highly relevant for advanced study and professional applications.